Ladies and gentlemen, welcome to the second part of this webinar exploring the transition from analog to digital electronics in physics experiments.
Let's now examine in more detail the digital pulse processing algorithms implemented in the FPGA of the waveform digitizers, noting the parallels with the traditional analog chain. The first DPP algorithm we will look at is called PHA, and it is designed to acquire the pulse amplitude from a charge-sensitive preamplifier. Typically, the PHA algorithm is used with semiconductor detectors such as silicon or HPG detectors, but it also works well with signals from scintillators coupled with PMTs, provided that the sampling frequency of the ADC is sufficiently fast for the decay time of the PMT pulses. In general, we can say that the PHA algorithm works with exponential signals, typically with a rise time of less than 100 nanoseconds and a decay time usually in the range of microseconds, but can go down to a few tens of nanoseconds. Therefore, there is no need to sample the signal at very high frequencies. Typically, a sampling rate of 100 megasamples per second is more than sufficient. It is, however, important to have an ADC with good resolution, at least 14 bits. The waveform acquired by the flash ADC is processed online continuously and without interruption by the FPGA. There are two branches of processing. The first one is the fast timing filter and discrimination algorithm. The purpose of this block is to identify the input pulses and generate the self-triggers. The timing filter includes a derivative component that removes the baseline and isolates the voltage steps, followed by an integrative component that reduces the high-frequency noise. The output of the timing filter is a fast bipolar signal that is compared to a programmable threshold to arm the trigger, which is then generated at the zero crossing point. The second branch is the trapezoidal algorithm for energy measurement. This block serves the same purpose as the shaping amplifier and peak sensing in the traditional analog chain. Its aim is to transform the exponential signal into a trapezoidal shape, from which the pulse amplitude is extracted at the flat top. The duration of the trapezoid can be programmed, similar to the shaping time of the shaping amplifier. A longer duration, that is a greater integration, leads to better energy resolution. However, the trapezoid duration also affects the probability of pileup between two trapezoids and therefore impacts the dead time of the acquisition. It's important to note that the dead time is not related to the ADC conversion, which occurs continuously without interruption, but it is related to the processing algorithm, that is the mathematics of the trapezoid formation. The DPP-PHA algorithm is capable of acquiring the time stamp of the pulses, thanks to the self-trigger generated by the timing filter algorithm, their amplitude through the trapezoidal algorithm, the input and output count rates, ICR and OCR, respectively, of pulses before and after pileup rejection, and if necessary, even the raw waveforms of the sampled signals. However, the transmission of raw waveforms incurs a significant data throughput, and it is typically used only for specific applications or during system tuning to monitor the behavior of signals, including those generated internally by the digital filters. The following figure shows some examples of trapezoid formation. The blue trace represents the output of the preamplifier, which is the analog signal sampled by the ADC and processed by the DPP-PHA algorithms. A sequence of stacked pulses, P1 to P7, can be observed. The red trace shows the bipolar output of the fast timing filter and the self-trigger generated at the zero crossing. As can be seen, the first 5 pulses have been correctly identified and will be counted in the ICR. However, pulses P6 and P7 are so close to each other that the timing filter, although fast, is unable to discriminate them. The filter will perceive them as a single pulse, as there is only one zero crossing, resulting in a deficit in the ICR count. This deficit can be statistically recovered in post-processing, considering the known dead time of the fast filter. The green trace shows the trapezoid formation of the pulses and the corresponding point on the flat top where the signal height is measured, providing the energy information. As can be observed, the energy can be determined for the first 3 pulses, and even for P2 and P3, despite the overlapping trapezoids. However, for P4 and P5, the distance between them is too short, causing their trapezoids to overlap in a way that makes it impossible to determine their heights. This condition triggers the pile projector. Consequently, for P4 and P5, we will have time and ICR count information, but no amplitude information. Therefore, they will not be used for energy spectrum and OCR count and will increase the dead time. In the case of P6 and P7, since the fast filter does not discriminate them and perceives them as a single pulse, the energy filter considers them as a single trapezoid with an amplitude equal to the sum of the two overlapping trapezoids. In the energy spectrum, these events contribute to the sum peaks. The only way to attenuate, but not completely eliminate, this effect is to analyze the shape of the output pulse from the fast filter, as it can be easily recognized as a double pulse, despite having a single zero crossing. However, this requires a rather complex waveform analysis that typically cannot be done online by the FPGA. That's why there are cases where saving waveforms is important.
The second section of this webinar is now completed. Stay with us for the third part.